Hello, everybody. Allow me to welcome you to our very first webinar series from IQS Nano. Right now, you should be able to see our presentation. Probably you also see us. So first, the introduction are necessary. So next to me is Milan Matějka, our CEO and expert in micro and nano fabrication.
Nice to meet you.
And my name is Vojtěch Schánilec. I'm product solution specialist at IQS Nano. Today, we will have a rather overview webinar prepared for you, where we will introduce you to our company, the technology behind our printer and the applications. And in the end, we have extra special guest, Lukáš Zezulka from Brno University of Technology, who will introduce his project, where he utilized the powerful tool, which is the IQnano3D printer that we provide. So without further ado, let me to give a word to our CEO and start a presentation.
Well, thank you, Wojciech. And I would like to begin with a brief introduction of our company. So we are a company located in the heart of the Europe, so in the Czech Republic. We have two facilities there. One is in the neighborhood of the capital city of Prague. And the second, from we are now speaking it's in the neighborhood of second largest city. It's Brno, so one of the most innovative region actually in Czech Republic. And our company, it's focused mostly for the micro and nano fabrication technologies, how to use them, how to utilize them, how to fabricate out also tools and devices that can be used in the microfabrication process. This webinar will be mostly about our IQnano3D printing system, which is based on two-photon polymerisation or two-photon lithography. So first, let me introduce overall the technology, what we will be talking about in the next minutes. So two-photon lithography, if you are familiar with that, IQnano3D system also belongs in this category. It's a technology which takes advantage from the lithographies. So this is planar technology which can write with high resolution and high precision, but typically with very limited type of objects, and also additive fabrication, so 3D printing. So two-photon lithography and our system as well, it's kind of bridging technology which can be used because it utilizes the high resolution, also the capability of 3D printing. And also it can fit a relatively large area of 3D printing tasks from low resolution to high resolution. Why it is able to do so? It's because of this. So we are using the system can be mounted with different lenses, and each lens can produce different type of focal spot. And because we are using femtosecond lasers, which can introduce the two-photon absorption, and after that also two-photon polymerization, typically in photosensitive material, then we produce in focal spot some kind of voxel, some kind of volumetric voxel, which size we can change by changing the lenses, or slightly also by changing the parameters of the laser or exposure doses. So that gives us quite large flexibility to start the printing process with the resolution starting somewhere around 100 nanometers, going up to several microns. So how the printing process looks like? So if we have some simple 3D object like this cross, it needs to be divided typically into layers. This is done typically by the slicing process. And then you need to write the objects, typically layer by layer. And in our case, we write it by the voxel by voxel. So it's important to have some kind of parameters we can set for each of the lenses or for the printing process, which is seeding distance. This is the distance of the focal spots or the voxels in the horizontal axis, and slicing distance, which is the distance in the z-axis or vertical axis. So if you want some high precision object, we can even introduce more layers, so more more precise slicing, but typically at the cost of the recording time. So these are the two main parameters which are used in a two-photon lithography process. Now more about our system. So our two-photon lithography system or two-photon polymerization system is called IQnano3D. It's one of the world's fastest system with printing speed up to 3.3 megavoxels per second. This is due to very unique and high speed principle of the deflection we are using, which is completely in-area free compared to galvo scanners, which we are not using at all. We can achieve very high printing precision and printing resolution, so we can achieve in minimal features below the 110 nanometers, like you can see on this bridge test. And that's because we are using the system which is based on the femtosecond laser with 515 nanometers laser wavelength, which will produce better resolution than typical near-infrared femtosecond laser. It's typically better by 20 to 30% with high resolution. We offer this system as a solution for flexible 3D macrofabrication because it can cover some tasks from very high resolution prints for micro objects, but also for the meso-size objects. As I explained on the lenses, simple exchange lens, and we can print with different resolution. We offer this system as the complete solution, so it's not just the device, but it's also printing materials, softwares, training, and also possibility to customize the system according to customer requirements. This is just the basic technical parameters. So we have the floor standing system which is using the femtosecond lasers, 550 nanometers. We have this quite unique acousto-optic deflector system. We have the printing area about 50 by 50 millimeters, and we are using very high precision stages in both horizontal and vertical axes, which can cover very high precision of the printing with precision below 100 nanometers. So what is the advantages of our system? So definitely it's a very high printing resolution. We can really achieve below 150 nanometers. We can produce high aspect ratio structures, which could be very difficult to achieve by conventional lithography, even the grayscale lithography. What is also unique in our system, we can print on the devices, so we can print on the microchips, in microfluidics on the device, because you have to choose of the printing plane you will like to print on. So this is perfect for the mix and match processes. Definitely, we can print not just the planar or 2.5D structures, but even the very high complex 3D objects. We can print with very high precision shapes and angles, which could be very beneficial typically for the optical applications. And one of the great benefit is for this area of optical applications is free-form structures. So we can combine different type and heights of the relief just by the single print. So how the workflow for the system looks like. So at the input, we have typically some data. It could be a CAD model from any CAD type computer software, but it could be bitmaps. It could be even customized script, and or you can use our special library for the simplify objects from which you can build your structures. We have our own software environment, which is called IQdata and IQwriter. IQdata is for the data preparation. IQwriter is for the control of the system. And then you need simply just to load the substrate, use the printing resin, and at the end you have your printed device on your substrate. So how the printing process looks like. So this is just an example. We have some substrate which is on our precise stage. We have the lens which is dipped in the photocurable resin. and we can move with the lenses like this, and together with the beam deflection or the movement of the substrate. And if you look in the more closer look, then you can see the writing process. What you can see in the video, that was actually our unique flying stage printing mode. I will be talking in a minute. So we have some basic printing modes. One is called flying stage, one is called step and repeat, for which could be a different type of data inputs. But we have many more of the printing modes or the parameters which can be set for both of them. And we will be talking about that in some upcoming webinars, because we don't have enough time for that. But we'll leave it for the next webinar. But let's just see how our two basic principles of the writing works. So one of them is the flying stage, when we are moving with the sample and we shoot with the lasers to the moved sample. The stage is moving or the sample is moving, and we fastly deflect the laser beam in other axis, so we can cover very fast large area. Typical for this mode, it's some kind of strips. So you can see stitch only in one axis, and we have some special strategy even to hide the stitches. Yeah, so we call it random strip, when the strips are moved during the printing process. This is typical or very similar to classical 3D printing, when all the object it's printed layer by layer. So we always print one layer completely for the object, then we move up and print another layer. Another printing mode is step and repeat. This is well known from typical lithography approach, when the 3D printed object is divided to the printing fields, in which we always cover all the printed layers by using our XY acousto-optic deflector, and then we move to another field. Again, we print another part of the layer. If there is some objects which are larger than the range of our very precise piezo stage in the Z-axis, there could be some stitching by movement of the lift to the another area. This mode is, I think, most typical, but its use for some special application could be very beneficial when you have small objects which can be covered within the writing field. About the softwares and tools, as I mentioned at the start, we have some IQ Data and IQ Writer environment for the user to control and prepare the data. The IQ Data, it's our solution which is available even offline, so it doesn't have to be prepared directly at the computer which drives the system, but the user can prepare their projects or the jobs in their offices, and simply just load the project to the device and run the printing. We will look more closely to functions of the IQ Data now, and also for the IQ Writer. IQ Writer is actually a system to control the printing process and to do some focus alignment, and basically is to run your projects or the jobs. In the IQ Data, it's included tools like a slicer, where you can input a 3D file like STL files. We have included basic model functions, so you can make rotation, resize. You can also have prepared pre-slicing parameters. So if you choose simply by clicking on the lens, then you will get presetting for the slicing and seeding distance. So even for the basic user, he don't have to think too much for that, but we give the opportunity to the user even change these parameters if they want. Yeah, and if in the slicer we have also function, if there is objects which are too large for the print, we can have subfields fragmentation to smaller subjobs. Our another part of the IQ data, it's something we call project builder. So you can see the printing plane in the middle, where you can put your jobs or subjobs. So it doesn't have to be only one printing jobs, but you can add and mix some printing tasks or subjobs. You can visualize the structures you want to print, and you can even have access from this part of the software to write your own scripts, which could be like Python or C++ based scripting. We have also vector-based job builder included in that tool. And in this module, you also choose the printing material from the databases, where is the printing parameters like exposure time, connected to the chosen material, and also you will choose the printing plane or substrate for which will be used during the printing process. The IQ writer, it's another part of the system where you can have access to look to chamber camera. You can select the lens. You can for advanced user, you can even change the lenses or another lenses if you want. We have some print or project list queue where you can have some more projects which could be loaded, which could be printed each after another. And of course, you have access to some settings, movement with the stage, laser control for presetting of the system before print is run. I want to mention also we have a very unique autofocus system, which is well automatical, and for the loading it's semi-automatical. So we can even print on a slightly curved surface because we can cover this by special autofocus routine during printing process. One thing I want to mention as well, and I was mentioning, we have also our printing materials. Compared to other companies, we have open material policies, so even you can use your custom materials in our system. We won't be give you any restriction for that, but we offer for the customers specially tuned material which will work perfectly with our system, and it's tuned to our laser wavelength by sensitivity and other parameters. So at the moment, it's just 3 materials: a basic one, a hybrid one, and a big buy one. The basic one is our choice for typically for proving of the design or rapid prototyping. It's a perfect material if you want to test your design and then print it maybe from some advanced material. More advanced material. It's with good adhesion to typical substrate like silicon or glasses, and it has a very high printing speed and resolution. The hybrid one is our solution for advanced engineering, so it's very tough material with high chemical resistance and very low shrinkage, which is great during the printing process, and with very good adhesion to the classical semiconductor substrates. And it's also material which can withstand very high temperature, so it's suitable for another processing like electroforming or materials depositions, so should be able to use for that. And Y1, it's our material we developed for the biomedical application, especially for tissue engineering. It's our material which is non-cytotoxic according to ISO. Very unique behavior is also low autofluorescence, so it doesn't have this yellow-green color which typically the resins has. So it's very transparent and can be used, for example, even for the fabrication of microfluidic devices or anywhere where the contact with the living cells is necessary. This material even can withstand high temperatures, so it can be used repeatedly, could be sterilized, could be autoclaved or sterilized in ethanol. So that's all about the basic of the material, and I think I will now give the word to Vojtěch. He will introduce some application area of our system. And what is it?
Thank you. So I just realized that I forget one crucial thing to mention at the beginning. The chat in this webinar should be disabled. However, you have the possibility to ask the question in a Q&A section in the Teams. And we have our other colleagues who are expert in the technical or sales areas, so they will be more than happy to answer all your questions. However, you can also ask or send us the question after the webinar via our emails. And now for the application areas. So we strongly believe that our IQnano3D printer has its immense use in these following applications areas. So in the medical and tissue engineering, thanks to the ability to print the complex objects, we are able to print scaffolds, as you will see on the next slides. We can easily modify the surface or functionalize the surface and create metamaterials, which can be usable from the cleaning of the water up to some optical manipulation abilities. We can print directly into the microfluidic chips. Thanks to the ability to print with the freeform surfaces, we are able to print flat optic devices, and not only flat optic devices, but 3D optic devices as well. And of course, some advanced high-tech stuff like, for example, MEM chips. We cannot print with a conductive resin. However, we can easily print we can easily print onto the MEMS chips with some mechanical devices. Here at the bottom, you can see the 6 main advantages of our system. As I will go through the various applications, I will highlight the ones that are necessary for the application. However, you can all the time use all of them. So first, 3D scaffolding for tissue engineering. The artificial 3D scaffolds are extremely useful platform for controlled environmental of cell growth. So the goal with the scaffolding is to be able to strictly control the architecture of the scaffold, since individual cells requires different type of scaffolds. So, for example, if you would like to grow the kidney cells, you probably would have to have like 25 different structural layer in one scaffold. Here, the solution is quite easy. With a two-photon polymerisation technology, you can control and create customizable scaffolds with high homogeneity, and you can do that repeatedly. Here on this image, you can see one of the scaffold we printed with the printing parameters. However, what might be worth to say as well, here is the output of the fluorescent microscope scanning the cells that grown on the scaffold we printed. As you can see, there are black crosses in the middles. Those are the areas where the scaffold is printed. And we want to showcase that the bio one, the resin that we use for this, has a low photofluorescence, so it will not interfere with your data. Another application is to print advanced drug delivery system. So basically, right now, we are able to print devices that helps the pharmaceutical industry to improve the therapeutic outcomes of the treatment, especially by being able to scale the delivery of the active pharmaceutical particles. So the goal is to develop methods for drug delivery. Here, this microneedles, they are quite sharp and stiff, so they can penetrate easily your skin just into the right depth to deliver the active pharmaceutical particle without any pain. We printed several of these batches. This one I will not acknowledge or deny that we use it on humans, but you can see here on the skin of our CEO that it kind of works, and he said that it didn't hurt that much. Another application we have is printing the microstents or implants. So basically, those are devices that should ensure structural support in the body. The goal is to manufacture precise control, hard and biocompatible implants that can be put into the body. For that, you need to be able to print complex designs and sometimes with high aspect ratio. Here you can see that the stents that we printed were tall, somewhere around 3 millimeters. And the solution, again, if you are using the two-photon polymerisation technology, you can easily design customable implants. You can easily test the designs with fast prototyping, since the printing doesn't cost that much and it's quite fast, so you can optimize your designs. We also printed some much smaller implants. That the one that I showed you before. This is an implant that can be put inside the eye to relieve the eye pressure. Concerning the integrated microfluidic printing, so basically you use microfluidic chips when you want to see how small amounts of liquid interact with its surroundings and so on. We can modify these microfluidic chips and functionalize them either by having a filtration systems, or for example some scaffold grown into the chip. It's especially important in biological research, in drug delivery system, because you optimally can grow individual cell, personalized cell onto these microfluidic chips, and use this as a test playing ground for specified treatment of individual. Again, we are able to print directly into the microfluidic chip, as you can see here. Thanks to the ability to print onto the device, you can see that we were able to print the filtration dam directly inside the microfluidic channel. The print didn't took that much time. It only concerns the dam inside the channel. The scaffolds behind took another 6 minutes, I think. I mentioned flat optics. So basically, flat optic systems are used to operate with the light, to control the light scatterings. Hugely important, for example, in automotive industry. The goal here is to innovate and to create new devices for optical control with high precision and possibly on the large scale. So the two-photon polymerization, because you are able to print free-form surfaces and different shapes and under different angles, we are able to print integratable structures and scale them up to the large production for individual applications. For the high-tech micro-optic devices, here you can see a system of the lenses. These systems can be integrated onto the wire and use it as in some high-end optical devices, or even in pharmaceutical for different probes. Basically, the goal is to be able to shrink this detection caps and be able to integrate them effectively with the device if you're choosing. Again, we can print on the devices. We can design complex structures, even complex structures that focus the lights. Basically, the only limits is what you can design. And yeah, there are some more limits, but let's not talk about them right now. Sorry. So for the high precision components, just to show you that we don't have to print only the small components like you've seen before. Here we have a knot and the matrix, but even though it's a quite microscopic object, we were able to maintain sub micrometer resolution, and these mechanical parts. Sometimes you need to print the mechanical parts with exceptional precision. You need to test the designs, and even in the case that you don't need to have these mechanical parts printed from the resins, you still need to be able that your design works. So rapid prototyping with this technology for the small batch production is the way to go before you scale your production on a much high-end fabrication devices. And the last but not least are the micro devices. So basically, similar to the previous application, you are able to print any micro component device that you design with a high precision, with a complex instruction, which can be then integrated into the microsystems of your choosing. With just to again highlight, you are able to fastly optimize your design to save money and time on the development of these objects and integrate them, because we are able to print them directly onto your device. Now, I would like to see whether there were any questions from the audience during the webinar. If they were, I hope that my colleague answered them all. But in case, yeah, we have. Thank you. So our colleague picked some of them for us to answer. So one of them is, you have mentioned biomedical application. Are you offering a system with laser other than 550 nanometers? So the answer is that a device with a 780 nanometer laser can be built upon a request, therefore the red laser. And we just want to emphasize that it's not the standard machine that we are selling, but we have many experience with red laser based equipment. And what is the maximum height and depth of the structure? So at the moment, the maximum height of the structure is 20 millimeters. Okay, I read nanometers, so I was surprised. No, it's 20 millimeters. Anyway, the printing process would take a long time, but that can be optimized with using the right optical setup. And do you offer print-on-demand service or just the whole system? So we are open to cooperation with you. So in case you have some interesting application that you would like to try, please write us an email, and we can find the most suitable way how to fulfill your desires, basically. So I would like to thank all of you for coming to our first webinar. As Milan mentioned, next year we will have a series of webinars where we will be diving more into depth of individual section, either the application or specific applications areas, but also the software itself and the technological background of the machine. If you have any other questions or ideas about what would you like to hear at our webinar, you can always reach us via LinkedIn or our emails, and we will be more than happy to have an open discussion with you. For today, that's all from us. Thank you all for coming.